Hi, can you hear me?
Yes, sir.
Just 1 minute. Okay, so yeah, last day of this year, and we'll start something new next year, hopefully. Uh, I don't know what you want to do today. I can continue with the topic of transformations. I mean, there is one question which I definitely want to discuss today, which I will do, related to that equilateral triangle problem that we had talked last time. But apart from that, we can relax and enjoy something different if you want. So I don't know. Up to you. Do you want to study geometry? Do you want to solve some puzzles, or what else? Anybody has any puzzles to share? Any riddles? Okay, if not, then I'll take geometry. I don't have any problem. So,
Excuse me, sir.
yes, go ahead.
Can we do something related to coordinate geometry?
Got geometry. Okay, sure. Yeah. But you know what, Anushka, that will be a entirely new topic on its own. What I can do if you want is after we finish transformation, we'll start with coordinate geometry in great detail.
Okay. Okay, sir.
Yeah. Okay. I'll just have to wait for 1 minute while my tablet is starting. But yeah, maybe just to talk about something else. So till yesterday we had the InMo training camp, which some of you attended. So I hope that was useful activity for you. And I mean, for those who were not able to attend that, we can still, I'll check if we can share the material from that for your reference, so that at least you know what topics were taught over there, and what practice problems you can try at home. So it's taking a while. Okay. Well, fine. Okay, so just to continue from where we had left last time, we had only one transformation left to be studied, which was spiral homothety. And so let me just quickly talk about that. In some ways, I'll say this is the most interesting of all the transformations we have studied. So it is worth taking some time understanding what is spiral homothety, what are its applications, because believe me, this is the most out of all the transformations we have seen so far. Spiral homothety is the one which will have lots of applications. Even in context problems, like in Olympiad problems, you will see a lot of usefulness of this idea. Okay. Okay. And as such, actually, it is just a combination of two other transformations we already seen so far. It is actually just a combination of a rotation plus a normal homothety. Okay. So basically, what you need to do is you like to rotate one object and then dilate it, either increase or decrease its size. So that is what spiral homothety is. So to define a spiral homothety, you need to know the center, that the center around which you will do the operation, and both the rotation and homothety has to be done around the same point. Okay. Then you need to know the angle of rotation, that how much angle you are going to apply. And then finally, you need to know the ratio of the dilation, right? So if you know these three things, then you can define this operation. And so the way it goes is that, so what is your center of the operation? Let us say you're applying it on some triangle over here. Okay. So first thing that we will do is apply the rotation. And actually it doesn't matter what you do first. So we'll see that. Let us say we do the rotation first. So around the point O, I will apply a rotation of angle theta. So that maybe this will go somewhere over here. Okay, so this is theta. So after rotation, maybe a triangle looks something like this. Okay. And after that, you apply the homothety of ratio k. So let us say that k is, let us say, greater than 1. Okay, so let us say k is 1.2. So we'll be roughly dilating the size of your object by the ratio 1.2. So maybe something like this. Okay, so that is all that is there in spiral homothety. That there is a rotation followed by a dilation. Okay. And you may observe that if you do the reverse order, let us say we do the dilation first, followed by rotation, it doesn't matter. It is still going to give you the same result, because suppose you do the dilation first. So the original triangle you first dilate with the ratio 1.2. So you'll get a new triangle like this maybe. And now this triangle you rotate with angle theta, but it is going to go and land in the same position. So whether you go this way or this way, the result is the same. Okay. Or I mean, if you wanted to state this in terms of the group theoretic notation that we have developed so far, that the rotation uh, and homothety are commutative, right? Or rather commute with each other. That is the better way of saying it. Importantly, this only happens if their centers are identical. Okay. So what do I mean by that? Here, the same point O is used for the doing both operations, rotation and homothety. If you had a situation where you have two different points, O1 and O2, and you do rotation around this one and homothety with this one, then it will matter what is the order. But only when the centers coincide is the homothety. I mean, these two operations are commutative. Okay. So this is a very important condition. And I wonder if the converse is also true, that given that some rotation and some homothety are commutative, can we prove that their centers have to be identical? That would be an interesting exercise for us to think about. Okay. So what is the significance of this spiral homothety? That why do I say that this is such an important operation? Uh, because what we'll realize is that, see, when we talked about rotation, we discovered some very important property that were given two congruent triangles. If you remember, we had done this point in the class to good detail, that if we have two congruent triangles, we had asked the question, does there exist a single rotation to take the first triangle into the other one, right? So do you remember the answer to this? That can we, any two congruent triangles in the plane, can we take one into the other in a single rotation. Anybody remembers?
No, we can't.
We can't, right? And I mean, the reason is because the order may be different, right? The suppose we have triangle ABC like this and triangle DEF, which is the what we call the orientation is clockwise or anti-clockwise. So if that changes, the rotation cannot do anything. But if I just add that word that given to similarly oriented, okay, so that I'm guaranteeing that the order is not going to get reversed. Then the answer is yes. Okay, right? That is what we had done in the class. That if I have triangle ABC like this and any other congruent triangle DEF, okay, then there exists a rotation. Oh, yeah. I mean, there is also one problem here that if the triangle is parallel to itself, right? And basically, a triangle which is parallel will require translation, but a triangle which is not parallel will require rotation. But I'm washing over that point a little bit by saying that you can think of a translation as a rotation from an infinite distance, right? In some sense, if you can imagine that there is a point which is at very far away, like at infinity, and from there you do the rotation. In some sense, it is like a you can start to imagine that as you take that point of rotation farther and farther away, that rotation starts to look like a translation. So in that sense, I'm kind of generalizing a little bit. So ignoring that point about the parallel thing, this was an important point about rotation. So very similar thing happens for spiral homothety. That now if I give one again similarly oriented similar triangles now. Now we no longer need congruent triangles. Okay. So if I have two similarly oriented similar triangles, I can ask the same question. Does there exist a spiral homothety that will take the first triangle to the second one? Okay. And again, I mean, barring some special cases like where a translation is required, in general, the answer is again yes. So again, if you have a triangle like this, ABC, and another similar triangle, DEF, okay, so similar, it's not necessarily of the same size, but has the same shape. Then we can try to locate the spiral homothety, which takes this triangle into the other triangle. Okay, so I'll maybe pause for a few minutes and ask you to think about this. That how will you find out what is the spiral homothety, which will convert the first triangle into the second one? So what we're interested is to locate some point O in the plane. And let me just roughly estimate where that will be. Maybe somewhere over here. Okay, so this is the point O which I want to locate, such that around this point O, some suitable angle and ratio will convert a triangle, one triangle into the other triangle. So first thing, can we find out what is the angle and the ratio? Even if we don't know where the point O is, we know the triangles, right? The starting triangle and ending triangle I know. So can we estimate the ratio and the angle? So we can do that by comparing these two triangles, right? So for the ratio, what I can do? If I compare any side of the any corresponding side, right? Like basically DE upon AB will be that ratio K. Whatever is that ratio of homothety will be DE upon AB. Okay. So I know the ratio. In the same way, can I know what is the angle? And let me write here, instead of D upon AB, let me write BC upon EF. Doesn't matter, right? Any pair of corresponding sides will be okay. Look for the angle. What if I join the lines BC and EF, right? See, when the spiral method is applied, this whole line BC gets rotated, right? So looking at this, can we say that the angle formed between these two lines is going to be by angle theta? And now here you may have a question that there are multiple angles. That this is also there, this is also there. So which angle should we choose as my angle of rotation? So how can you answer that question? That which of the two angles should be taken as my angle of rotation? Because if you think about it, this line BC can be rotated into line EF in two different ways, right? I can either rotate it clockwise by some small angle to make it like this, or I could rotate it anti-clockwise to make it like this. So which of the two should be considered?
The first one because it is in the same orientation.
Aha, correct. So, or whether one way to put it, I'll say that if you think of BC not as a line segment, but with a vector, right? So there's a direction, right? Going from B to C, there is a direction associated with that. So we are not rotating just one line segment to another line segment. The correspondence is important. So we want B to go to E, right? And C to go to F. So we are interested in the angle between these two directions. If you rotate it like this, what will happen? The original vector, which is like this, will become like this. So then your points E and F will be in different order. Your E will be here and F will be here, which is not what we want. Okay, so that is why this is the right one, this is not the right. Okay. But in general, I mean, for more complicated figures, you have to be careful that which of the angles you choose. But the point is that we can find angles, right? So the angle formed between the lines BC and EF is my angle theta. So I have both these quantities available. So only thing left is to find that actual center of homothety, which is the point O, right? So for this, what we observe that because of the homothety, can we write some relations between the point O and these two triangles? Like let us pick only one point. Let us focus on the point B. Okay. So if you understand how we are applying this operation, right? So first we are going to rotate B to some new position B dash, right? Through angle theta, correct? And then B dash is the one which is going to dilate with the ratio K to E, right? So what can you write any relation between these 4 points B, O, B dash, E? What are the angles formed? What are the distances formed? Like angle B, O, E is theta, right? And what else can we say? What about the distance OB and OE? Can I relate that? Because I know the ratio of homothety. So I know that OB and OB dash are equal. and OB dash and OE I have the ratio K, right? So can I also say OE upon OB is equal to K, right? So ratio OE upon OB has to be K. So if I know these two things, can I find the locus of this point O? Like looking at the first part, if I know this angle BO is theta, then does that give me one possible locus of the point O? Because what are all the points in the plane for which this angle BOA is constant? Whenever you have any 2 points, right? Suppose you have any 2 points P and Q, and you know that the angle formed by them with some variable point x is theta, then what is the locus of this point x?
A circle.
It is a circle, right? It is a circle where the central angle is 2 theta, right? So if you want to construct this, you can construct the central angle of 2 theta, right? And if I use that as my point of drawing the circle, like center of my circle, and draw a circle, actually it should be a circular arc, I'll say. So the circular arc like this is px theta. But if you consider directed angles, then it will become the full circle. Like if I consider directed angle pxq is theta, then it doesn't matter whether the point x is on this side or this side. Okay, but depending on whether you want to work with signed or unsigned distances, it will be a circle. Um, Okay. Or so actually there are two ways of considering this. Whether you are talking about the directed case or undirected case, the answer will be slightly different because if you are considering undirected case, then when you have points P and Q like this angle is also theta and this angle is also theta. So in that case, your answer is actually two circular arcs like this, right? Symmetrical around the BC, the PQ. So in the undirected case, you have to consider two congruent arcs on both sides of the segment PQ. And in the directed case, you have to consider the full circle because there the direction matters. So there it will be only this one. Okay. So here, for example, if you think that this is also theta, but actually if you think about it, it is minus theta, not theta in the directed case. So depending on whether we are talking about directed or undirected, we have to take that into account. For now, let us work with directed angles. So therefore, we are going to consider a circle. Okay, so then, so can I draw the circle uh, on points B and E such that the angle BOE is guaranteed to be theta, right? So I can draw that circle. So I know that my point O, the center of homothety has to lie on this circle because this angle is theta. What else can I draw?
So this theta is not the same as the theta between EF and BC, right?
Yeah, it is the same theta, right? Why not? Because if you look at here, this is a it is the same theta. Why not? Actually, my diagram doesn't make it clear, but yeah, maybe I should redraw the diagram. The circle is going to pass through this point. It is going to be a cyclic quadrilateral.
Then why is that angle PXQ also theta on the other side of the circle?
In the directed angle case,
Yeah,
okay, so maybe I'll just quickly talk about that. So basically, what are directed angles? Directed angle between when I let us say I have any point x like this pxq. So when I write directed angle pxq, which is also the same as writing the directed angle between two lines px and xq, and how we define it, it is the angle through which we need to rotate the first line to match it to the second. Right? So by how much we need to rotate this line px in order to match it with xq. That is what we call the directed angle. And we always do the rotation around the point x. So in this diagram, if you look at it, like what we call pxq, this angle, right? So I can either rotate it like this or like this, right? Both is fine. But by convention, we always use anti-clockwise as positive and clockwise as negative. So looking at this, roughly speaking, let us say this looks like 40 degrees, so minus 40 degrees, or it could be plus 140 degrees. Either way is fine. So I say the directed angle between PXQ is plus 140 or minus 40, whatever you want. Okay, so this is when the point X is on this side. Now, similarly, let me take another point on this side. Let us call it Y. Okay, so I am going to use the same definition to compute angle PYQ. Directed angle PYQ will be the angle by which we need to rotate line PY to make it same as YQ. So, in this diagram, can you see that around point Y, how much should I rotate the line YP to make it coincide with the YQ? Again, you can choose clockwise or anti-clockwise. Any direction is fine. If you do it anti-clockwise, then how much will this angle be?
Plus 140.
Right? And if you do anti-clockwise, it is minus 40. So you see the value is turning out to be the same. So the whole advantage of directed angles is you don't have to care about whether the point is on this arc or that arc. On both the major arc and the minor arc, the directed angle definition gives you the same result. So if this were not directed angles, then you would have to be, I mean, when I say that 4 points are cyclic, right? If I say that PQRS are cyclic, okay, then without directed angles, I cannot directly say that PQR is equal to PSR because I don't know the order. Like if the diagram is like this, if the diagram is like this, that PR is here and QS is here, then this statement is true, right? Because their PQR is really equal to PSR. But if I don't know the order of the points, what if the order of the point is reverse? That P PR is here and Q and S are like this. So now it's no longer the case that PQR is equal to PSR because in the normal angles, what happens is that the angle now becomes supplementary. So, but instead of the normal angles, if I say directed angle PQR and directed angle PSR, then this is guaranteed to be true no matter what is the order of the point. So in the first diagram also, you'll see that PQR is this angle, right? PQR is this angle and PSR is this angle. So they are equal. So they were equal in the normal sense also and they are equal in the directed sense. And now in the second diagram, again, PQR is this angle and PSR is either this angle, which is the supplement, or this angle. Okay, I hope this is clear to everybody that how directed angles solve the problem of the order of the points on a circle. Okay. I think we had discussed this sometime earlier, but maybe just need to revise it once more. You can go back to a few lectures from maybe August or September where I think we had talked about this. Okay. So therefore, this directed angle BOE, which we know, will give us this circle, which is the first locus. Um, how else can we determine point O? What other properties the point O has to satisfy?
Can you just explain why it was cyclic once again?
Okay. So here, if you look at the two, what we call this kind, sometimes they're called configuration, that there are two possible ways to arrange the points, right? So PQRS can be in this order, where PQSR, if I go in
Okay.
this direction, or they can be PQRS. Okay.
Excuse me, sir.
Yes.
So I'm talking about the previous diagram, like
This one.
BOE. No, the
Oh,
question
okay.
diagram.
Okay. What do you want to know
Yeah,
here?
in that y is angle BOE equal to theta. That one.
Why is it theta? Because O is the center of homothety around which I'm going to take the first triangle into the second triangle. So that whatever is my angle of homothety theta, see, first I'm going to rotate B to B dash, right? So when I do that rotation, there itself I'm going to have the angle theta. And then finally, second step when I do the dilation, which will take B dash to E, that will not change the angle. So from B to B dash and B dash to E, this is a two-step process. But out of that, the first step, which is the rotation, which we'll do around point O. That is why this angle is theta.
Okay. Fine. Thank you.
So can we find one more locus for the point O?
The circle with chord CF.
Correct. Because the same operation is going to take A to D, B to E, C to F. So why don't I change my point that instead of using B and E, Suppose I use the point C and F, right? I could draw a different circle, right? Suppose I take point C and F as my points. Again, this will also have the same relation that this angle will be theta. So I could draw a similar arc with a circle with center C and F, right? Okay. So where these two circles intersect, but the thing is they could intersect in more than one point, right? Like for example, in this diagram, uh, it seems to be that point, this point which I marked earlier, that will also be one point of intersection for these two circles. But that's okay. We'll get 2 points, and one of them will be the center of that homothety. Um, if you want to be extra sure that which is the actual center of homothety, you can take the third point also. You can take the point A and D and use the point A and D as the center to draw one more circle, and where that circle passes, that will be definitely the center of homothety. Maybe I have to answer the question, what if all the three circles are like coaxial circles, like all three of them pass through the same pair of points? Let us think what happens then. But otherwise, in general, that won't happen. So in general, you are going to get some point around which all these three circles pass, okay, with angle theta. Okay, let me just show this in actual practice, that how this looks in GeoGebra. So what we have is a triangle, and let us say I just draw any triangle over here. By the way, GeoGebra has a habit of taking the positive angle always. So I have to mark this. So I'll copy this angle alpha over here. Okay. Okay. And I'll copy the angle beta from here. Okay. So if I join these two lines, I'm going to get a triangle which is similar to my uh, original DEF. Right, call G. Okay. Let me hide these points. So I mean, if I change my original triangle, you'll see that my new triangle is always similar to that one. And so now let me just try to roughly set it up in a way so that everything remains nicely within the diagram. So I need to find a center of homothety for these two. So for that, what I need, I'll first measure the angle formed between BC and EF, right? So let me first join BC and EF. So this, if I look at this angle, right, the angle formed between these two lines is the one which I'm interested in. So like if I just mark it and give it some name, this angle gamma is the one which I'm interested in. So around points B and E, I need to draw an arc where this angle gamma is met. So if you look at it, there is one very easy way to do it quickly in the diagram, because angle BGE is already in the directed angle sense, it is already gamma. So why don't I just draw this circle through these 2 points? Okay. Uh, Actually, that angle is very large. Let me just move it. Okay, so this angle of gamma which is roughly 40 degrees. So this arc which you have got, right, major arc BE dash. This is the locus of that point O, because if you take any point on this arc now, and if you measure that angle BOE, it is always going to be that gamma 39 point whatever degrees. Let us make it a round figure of 40 degrees. Very Okay, so this is one locus, and if we repeat the same exercise with C and F, and again, very conveniently, this point G will give me that focus. So if I just consider the circle passing through C, G, and F, right? And so the second point of intersection of these two lines, which is this point, this will be my center of homothety. Let me call that. Okay, so my claim is that O is the center of homothety with the angle being 40 degrees, and we still don't know the ratio. So for finding the ratio, we just have to take the distance, like compare the length of this segment to this segment, right? So like if I just write, okay, so I have written is I upon F. So the length of this segment upon the length of this segment, which is roughly 2.44. Yes, that varies over. So if I take this as my ratio of homothety and gamma as my angle of homothety, I expect this triangle to go and nicely sit on this triangle. So let us see if that actually happens. And for that, let me convert this into a polygon. So I'm going to first, so let us do the rotation first. So I'll rotate this triangle around my center O. I have to do it clockwise with angle gamma. Okay. So this is the first step. So you see that OB has come to B dash. And now I have to just dilate this again with this point. And the factor is, what was the factor? T1, right? No, no, sorry, the factor was A. So you see how nicely it has gone and exactly landed on the target triangle. And so if I make any changes to my diagram, like if I rotate or anything, then this point O automatically changes its position. Okay. Uh, And I mean, just for completion, we could also draw the circle through points A and A dash, or and D. Now that has coincide with A dash now here. And that will also pass through point O and give the same angle gamma. Right? If I just mark it over here. Ah, this one. Yeah, you have to be careful about the order. Okay, so this angle is, again, if you look at it, this is 41.43 degrees, which is the same as the gamma which we measured earlier. Okay, but this is not all. So far, if I go back to my diagram, what we have made use of till now is only the first part, the fact that the angle formed by the center of homothety is a constant theta. But we also know the ratio, right? So can we use the ratio to get more loci? Let me just draw the diagram cleanly again. So suppose, I mean, I just take 2 points, B and E, okay? And I know that let us say I know the ratio of homothety is K, right? And so what I know is that this ratio OE upon OB is equal to K. Then can I use this information to find another locus?
The Apollonius circle.
Right, the Apollonius circle with this ratio, right? So to draw that, what you can do is if you join BE and divide it internally and externally, the ratio K is to 1, right? And if you take those 2 points as the diameter of your circle, then that circle will pass through O. So in fact, if you think about it, there are going to be not three, but six circles passing through O, because you can repeat this exercise for every pair of points, right? If you go back to a diagram here, just as OB upon OE is, or rather OE upon OB is K, in the same way, the other ratios OD upon OA and OF upon OC, they are also K. So you could draw the Apollonius circles on any pair of corresponding points with that ratio k, and that is also going to pass through, right? Yeah, I'm just thinking, can we do this in geographically? Uh, how do you draw the Apollonius circle of 2 points and a given ratio? Uh, we have dilation. Suppose let me just draw the Apollonius circle for points B and B dash. Then let me just go to the drawing board for a moment. Like what I want to construct is P and E. So I'm interested in the internal point of homothety such that uh, so what I know is OE upon OB is K. So that will be equal to EX upon XP. Right. But I only have the dilation to level with me. So I need to determine EX upon EB will be K upon K plus 1. Right. So EX upon EB is K upon K plus 1. And the external point of homothety where BY upon not by, again I have to do ey upon yb is equal to k, but I want instead ey upon eb, so I can subtract the from this how to obtain ey upon eb. So if I do ey upon ey minus yb, that will give me ey upon eb, right? And so that will be equal to k upon k minus. Okay, so I need the ratio k upon k plus 1 and k upon k minus 1, and if I apply those ratios with E as my center, then D will give me x and y. Okay, so going back to triangle, so instead of k I have to take a over here. So okay, so let me use dilation. So I need to dilate the point B around the point E, and the factor is a upon a plus. Okay, so this b1 dash is the one point of the diameter, and similarly, if I again dilate b around point b dash dash with the ratio a upon. So b1 dash and b2 dash are the centers of the points, diametrically opposite points of my Apollonius circle. So if I just draw the circle with this other diameter. And you see that circle is also passing through O. I mean, it's not surprising, but good to see that that is happening. And you could repeat this exercise for all the other points also. So actually, you see that this point O will have not three but six circles passing through it. And to finish this problem, you could choose any of those circles that if you want, you can take two angle theta circles. You could take any combination of one theta circle and one Apollonius circle, or you could take two Apollonius circles. Any combination can give you the locus of the point. Okay, and so therefore this gives a definite way of saying that the answer to this question is also yes. Okay, I'll just add a star there because again I'm not discussing the corner cases. Like suppose that two triangles are parallel, right? Like they are similar and they are parallel to each other. Then what happens? So I think if even if the two triangles are similar and parallel, right, like this, then also the answer is yes, because now it will be just because they are parallel, there is no rotation required, just a homothety. But we can always say spiral homothety of angle 0. So there is no harm in saying that Yeah, then if I join this point like this, I will get the center of homothety. Oh, so it will be just the center. It will be spiral homothety with angle 0 and some ratio uh, k. I think where we land into problem if what if this k is also 1? Like if you have two congruent triangles, so congruent triangles are also similar. So if you have congruent parallel triangles, then we are in trouble. So that is the only case where we have to use a translation. But all either other cases, the answer is yes. So that is a small side note. Okay. So this is a very important fact that you can take any triangle into any other triangle with a spiral homothety. And we'll see how to use this in solving some problems. For example, last time I had mentioned one problem about an equilateral triangle. So let us look at that question in more detail. So what I had asked was that there are actually two questions, out of which one we have already solved with just normal rotation, right? So the first question was given two lines and a point, right? Suppose the lines given L1, L2 and a point P, then construct triangle PQR, which is equilateral, such that Q lies on the first line and R lies on the second line. So that we had solved with just rotation. We had just taken the, suppose these are the two lines and this is the point P. Then we had observed that since PQR is equilateral triangle, so if I apply a rotation of theta 60 degrees around point P, then Q becomes R. So the idea is why don't I apply that operation to the whole line, right? So if I apply that to the whole line and the line rotates, wherever it intersects the second line is the point R. Okay. So then what we said is that I'll change the question a little bit. Now what is given is not two lines at one point, but I've given three lines now. So now suppose I've given three lines, or in other words, I've given a triangle. Okay. So if I give you the three sides of a triangle ABC, and now I'm interested in a equilateral triangle where one point lies on each side. Okay. So I want one point here, one point here, one point here. Okay. So now here what will happen? See this point on the line AC I can choose arbitrarily because I don't really care which point I choose. So I could choose any point on the third line and I'll just ignore this line, right? Then this has become this problem. So basically I could choose my point P anywhere on the line AC and it would still solve the same problem, right? So which means that actually this question has infinitely many solutions, right? Like if I want PQR equilateral such that P lies on uh, CA, Q lies on AB, and R lies on BC, then this has infinitely many solutions. Because as you vary the point P on the line AC, you'll keep on getting different triangles. But what the question which I had asked was, out of all the solution, I want to uh, determine the triangle PQR with the smallest size. Okay, so size means the length of the side, maybe area, perimeter, any way you define size. So out of all those triangles, which triangle PQR will have the smallest size is the question. So anybody who has already thought about this problem and have any ideas? I mean, just to draw one more triangle, like let us say I call this point P1, Q1, R1. I could take a different point, maybe somewhere over here, P2. And if I repeat the procedure which I explained earlier, I'll get one more triangle like this maybe. And like that, as I vary the P1, P2, all the points on the line AC will give me one triangle. But which member of that family will have the smallest size? Okay. So to help us answer this question, what we studied just now will be very useful. That we are talking about spiral homothety and how it can be used to take any triangle into any other similar triangle. So do you observe something about these two triangles P1, Q1, R1 and P2, Q2, R2? Do we agree that they are similar triangles? Similar and similarly oriented triangles? So there has to be some point in the plane which can be the center of spiral homothety, which will take the first triangle into the second triangle. So can you try to determine that point of homothety? That what is that point around which the first triangle becomes the second triangle? And I mean, just to be clear in my diagram, the triangles are looking almost like congruent, but I hope you understand that is not the case. I could take this P2 Q2 R2 a little bit far away just to dispel that notion that we are not talking about congruent triangles here, we are talking about similar triangles. So like suppose I take uh, P2 over here, then you see now the second triangle will be quite larger in size. Okay, so now P2 Q2 R2 is like this. So clearly the triangles are not congruent, but they are definitely similar because, I mean, by definition, right, I'm talking about equilateral triangles. So how will we try to determine the what is the center of homothety? So we could do it using the what we discussed earlier. We could use some kind of Apollonius circles if we want, or we could use what we say angles, the arcs with the constant angle. Both approaches should be fine. We can pick any approach which we think is easier to trace. Okay, so let us say we want to go with the angle approach. So roughly speaking, let me just put the point O somewhere over here. We don't know where it is located, but I'm just placing it somewhere. So what we know is that, see, under this spiral homothety, P1 becomes Q1, right? Under whatever operation we are going to do. So therefore, the angle formed at the center, that P1 O Q1, right? This angle should be equal to the angle of the rotation. That how much, whatever rotation we want to do to take one triangle into the other triangle. So sorry, what am I saying? Not Q1, sorry. Sorry, P1 Q1 R1 is our original triangle and P2 Q2 R2 is my rotated triangle. So P1 will go to sorry, P1 will go to P2. So therefore the angle formed between P1 and P2 at the point O, that is the one I'm interested. So angle formed by P1O P2. If I know this angle P1O P2, then I can draw the arc uh, with center arc with points P1 and P2, and that will have the point. So can I determine this angle P1O P2? So same as what we had done earlier, we could take two sides of the corresponding triangles, right? So in this mapping, line P1 Q1 is going to become line P2 Q2. So in my diagram, look at this angle. So line P1 Q1, if I think of them as vectors, so this is my P1 Q1 vector, and that is going to become P2 Q2. So what is the rotation through which I need to take this? So if I'm marking this diagram, it is this angle, right? It is a clockwise angle. So in terms of magnitude, it will be negative, but let me just call it theta. So this angle theta, which is there in our diagram, is the same as this angle theta, right? And so knowing that angle, I can draw the arc around P1 O P2, and that will have this point. And the same angle theta will be involved in the other pairs also, right? So for illustration, suppose I talk about a different pair. Just as P1 will go to P2, Q1 will go to Q2, right? So this angle is also theta. So we can find this point O, right? That around the point O, if I do the homothety, spiral homothety, the triangle P1 Q1 R1 will become P2 Q2 R2 with some angle theta and some ratio K. But what we'll observe is that this point O can be used as the center of the spiral homothety to take P1 Q1 R1 into any other triangle of this family. So we are talking about an infinite family here. So just as P1 Q1 R1 P2 Q2 R2 are two members, any point I could take on this line, like if I take a P3 over here, so P3 will give its own new triangle, right? P3 Q3 R3. So the question is, every time I choose two triangles and I find the center of homothety, am I going to hit a different point every time, or it is the same point? So it turns out that it is actually the same point. So the same point O is going to be the center of all of these spiral homotheties. So going from triangle P1 Q1 R1 to P2 Q2 R2, or this one to R3, or even coming back from here to here. So any two members of this infinite family are related to the same. I mean, the angle and theta will be different, but the center of spiral homothet is always constant, which is this point. Okay. And why is that important? Because we are interested in finding the triangle with the smallest size. So out of all of these triangles, the triangle which will have the smallest size will be the one where if I take this O as my center and I draw perpendiculars to the three sides. Okay, so if uh, I have too many colors in the diagram, so forgive me, but I'll clean it up a little bit. So if I draw perpendiculars from my point O to the three sides, right? Then where those three perpendiculars land, right? Those will give me the best possible triangle. Okay, so let me illustrate this in GeoGebra. Then we'll come back to the proof of this, that how this is working exactly will not be clear in the diagram, but let me just show it in GeoGebra. Okay, so what is given to me is triangle ABC, and suppose I take any point, that this is my point P1. Okay, and so if I repeat the procedure of drawing the equilateral triangles with P1 as the center, I mean you know the procedure well by now. So if I rotate P1 uh, 60 degrees, right, where it meets the second line, this is my point R1, and so if I construct equilateral triangle P1 R1 as my two vertices, right. So you see nicely how the third point is going to lie on the third side. And so as I vary this point P1, I want you to observe. So this is the infinite family we are talking about, right? And out of this, we don't get this line. If I choose any two members of this family, so let us say this is P1, Q1, R1, and I repeat the process for a different point P2. Again, I rotate this line around P2, 60 degree. So I get the point R2. Okay. And again, constructing the regular polygon. Okay. So these are my two triangles, P1, Q1, R1. Let us say I take P1, Q1, R1 slightly smaller and P2, Q2, R2 as slightly larger. Okay. So, I mean, clearly the triangles are not congruent, but they are similar. And so what I'm asking us to find out is what is the center of the spiral homothety, which will relate these two triangles, right? So, where can I'm not interested in looking at the color of the interior side. No, this is better. So same as what we had done earlier, if I want to determine the center of homothety, I can look at two corresponding lines. So like P1, Q1 after rotation becomes P2, Q2. So the angle formed between these two lines has to be my angle of rotation, right? So this angle which is formed here, Q1, D, Q2, if I apply that same angle and I draw an arc around point P1, P2, then that will give me my locus, right? Okay. So my center of homogeneity has to lie somewhere on this circle. Okay. In the same way, if I take the same angle from point Q1 and Q2, Okay. So where these two points meet, okay, if I call this my point O, okay. So O is the center of homothety, spiral homothety, around which P1 becomes P2, Q1 becomes Q2, and R1 becomes R2. Okay. And so now see what is happening. If I change my two triangles, right? I'm changing P1 and changing P2. But even if I change the triangles to two different members, so I can choose any two members of this family, but the O is not changing. The center of spiral homothet is always the same. That is a very interesting thing that's happening here. Okay, the center of homothet is still O. It is not changing. But of course, we need to prove this. But I mean, I just wanted to illustrate that how this is happening. Okay, so why would the center not change? That what is so special about this point O that it does not change even when the triangles themselves are changing? And I mean, just to complete the proof that finally we are interested in the triangle where the size is the smallest. So to do that, what I'm suggesting is that, see, when this triangle changes, right? If you look at it, the line, the distance OP1 also changes. Like P1 goes far and P comes closer. But what if you consider the special position of P1 or let's say P2, where the OP2 is as small as possible. So when OP2 is as small as possible, where will P2 go? It has to be at the foot of the altitude, right? So yeah, if I from O, if I drop a perpendicular on any one side, right? So P2 is my foot of the altitude. So when P2 is here, so at this point, this polygon is the smallest of the smallest size. And if you in the diagram also it looks like that, right? If I take it on either direction, the distance increases. Uh, Maybe if I just so observe this distance 6.68, and as I was hoping to increase the decimal places, but see, it is like decreasing, decreasing. Here it is 6.57, and again it starts to increase. So clearly, this is the point where the this distance is as small as possible. Okay, so that part is not difficult to understand, but the reason why this works is this point O is fixed. That is the mystery that we have to solve. That why does this point O not change? Okay, so coming back to the diagram which we have. So let me just clean up the diagram a little bit and let us focus on what we want to prove here. So what we have is we are choosing some two points P1. Let us say the first point is P1, and I'll just draw roughly by hand. So P1, Q1, R1 is equilateral. And by the way, we are soon going to see that this equilateral has no special relevance. It could be any shape that you want as long as the shape is constant. So equilateral is just, I mean, by accident you can say that we are talking about equilateral triangles, but this could be very easily applied to any other shape also. Okay. So now if you consider another point P2, P2, Q2, R2 is another equilateral triangle. And so let us look at that point O in more detail. That the if I'll just directly plot the point O, and we are saying that around point O we have this spiral homothety. So OP1 and let me just change the position of point a little bit. Here it is looking very much like the center of the triangle. Now it is looking equilateral. I'm just choosing any position arbitrarily. Okay, so O is the center of the homothety, spiral homothety, such that uh, with center O and some angle theta and some ratio k, the what is happening is P1 goes to P2, Q1 goes to Q2, and R1 goes to R, right? And by what we had already done, like we know this angle theta is not some mysterious angle. We know exactly where that angle theta is. That is the same angle as the one between these two lines. So what I'm asking you to think about now is, can you find any properties of this point O which may help us to solve this problem? That why this point O does not change. It may be useful to try to find some properties of this point O. So think about that. So we have actually two pieces of information available to us. One is that the angles formed at O are all theta, but the ratio is also given, right? So let me write both pieces of information. So what we have is angle Q1O Q2 equals angle P1O P2, which is theta. And we also know the distances, like we know Q1O upon OQ2, which is equal to P1O upon OP2, is that ratio K. So we know these two pieces of information. On the basis of this, can you see some similar triangles in the diagram? Like which triangles have all of these quantities related to each other?
OQ1, Q2 similar to OQ1.
Yes, OQ1, Q2. So triangle Q1, OQ2 has to be similar to triangle P1, OP2 by AA test, like SA. What test? SAS test. SAS test of similarity. Because the exactly two pairs of sides the ratios are given and the angle between them is given. So these two triangles are similar. Q1 of Q2 and P1 of P2. And whereas the same thing will happen to R1 of R2 also. There is nothing special about P and Q. Same analysis can be done on the third side also. But for now we are focusing on P and Q. Any other triangles which are also similar? And this is an important observation. Whenever you have one pair of similar triangles, you always have one more pair of similar triangles. So, what is the other pair of similar triangles?
P1O Q1 and
Yes,
P2O.
yes, correct. Because this angle between is common, right? Yeah. So, if Q1 or Q2 is P1 or P2, can we also say that, like, if I just give some temporary name alpha, then this theta plus alpha is coming here also and here also. And you can just rearrange these uh, terms to give us the other similarity. Okay, so let me just write that here. So just as this similarity is there, the other similarities, angle P1O Q1 equal to angle P2O Q2, and which is equal to theta plus alpha in our diagram. And just rearranging these little bit, we can also write P1O upon P1O upon P2O. Okay, that, in fact, that is what we have written over here. So actually it should be reversed, that we use this for this similarity, and we are now going to use this for the other similarity which you said, that triangle P1OQ1 is similar to triangle P2OQ2. Okay, that's good. That's a good similarity to observe.
I think I got something.
Yes, tell me.
So like um, angle Q1, yeah, Q1 Q2O is equal to P1 P2O.
Yes, correct.
So A P2O Q1 is cyclic.
Correct. So because of the this similarity, this angle Q1 Q2O, this angle is the same as P1 P2O, which is this angle, correct? So therefore, if you look at triangle A, quadrilateral AQ2O P2, that is cyclic. Yes, correct.
So like similarly A Q1 O Q1 is cyclic.
Yes, correct. Correct. So
So so
yes, continue.
so like we calculate A P1 Q1, which
Hmm.
is equal to A O Q1. And like
AP1 Q1 is equal to AO Q1. Yes, okay.
and then we like calculate BR1Q, which
Yes,
is also come equal to BOQ1.
yes, okay.
And so like we get AOB constant angle because they are like related to angle C.
Yes, correct. Or rather, way I would put it is that in this diagram now, if you look at this, what we have obtained is, by the way, I hope everybody is following this, that how, because of the similarity, these two angles are equal. These two angles we show to be equal, and therefore points A, Q2, O, P2 are cyclic, right? So if I consider this circle passing through these points, A, Q2, O, P2 is cyclic. So the way I would proceed with the proof is, and what Om you said is also valid, but another way of saying the same thing is that there was nothing special about P2 and Q2, right? I could repeat the whole argument for Q2 and R2, and I will get the same result. So just as A, Q2, O, P2 are cyclic, A, R2 OQ2 is also cyclic, right? So I could draw another circle passing through these 4 points. And there's a third cyclicity also, which is not A, sorry, B. B R2 OQ2 is also cyclic, and finally C, I could use C P2 and R2 in the same way, right? So C P2O R2 will also be cyclic. And the key point is that in all of these, we are only referring to triangle P2Q2R2. In this whole analysis, we never had to refer to P1, Q1, R1. So the conclusion is that even if P1, Q1, R1 changes, these circles are not going to change. These three circles which we are drawn will remain constant. And so the point where they intersect, this O will also remain constant. So in fact, so there's a very interesting thing that generally speaking, to find the center of homothety, you need the starting object and the ending object. But here, what I'm saying is that if you have the starting object, like if you are given one triangle P2Q2 R2, that is sufficient to determine the center of homothety. The whatever is the ending object doesn't matter. That same center can be used to obtain that ending object. Okay. So again, to illustrate this in our diagram in GeoGebra. So in this diagram, we drew P2Q2 R2. For temporary, let me just sort of increase this size so that it is out of our coverage. So I'm focusing on only P1 Q1 R1. And so for this P1 Q1 R1, what I'm saying, we can determine that point O by just drawing this cyclic quadrilateral. So if I draw P1 A Q1, Q1 B R1, right? Oh, I think I chose the wrong point there. Hmm. So yeah,
So
I
we should
drew
select
P1 A Q1, Q1 B R1, and R1 C P1. Sorry, somebody
yes.
saying something?
Yes, like
Ah,
we
okay.
should select C.
Okay. I think that this other circle is not required. Hmm. Okay, so here, so what I'm saying, this is my point O, which we had obtained earlier. Let me call it. Yeah, we can call it O. And now what will happen? Oh, okay, actually I called this O. I already had called another point O. So let me call this point O2 temporarily. Okay. And now observe what is happening. I deliberately had taken the point P2 very far away, but let me bring it back into diagram. So you see, as now I'm changing the point P2, that point O1 which we had marked earlier, where is that point? We had marked the point somewhere in it has vanished. But basically it is the same point. This O2 is the same point as before, around which the homothety is being applied. Okay. So so the conclusion is that even if I change P1 and change P2, right? That point is going to remain constant, but because it actually does not depend on both members of the family, it depends on only one member of the family. And by the way, again, interesting thing you have observed in this proof, like if I go back to my proof, in the whole proof, we never made reference to the fact that PQR was isosceles. All we care about is P1 Q1 R1 is similar to P2 Q2 R2. So the same argument can be repeated for any shape of the triangle. Okay, so there is a special name for this configuration. It is called sometimes it is called Miquel. Somebody says Miquel configuration. Okay, this is the name of this configuration. So if you want to know more properties about this, you can Google this name. You will get the name. So typically, the way Miquel configuration is done is slightly different. They start with the cyclic quadrilaterals. Okay, so they don't start with the internal triangle. What the Miquel configuration typically does is like this. If you take any 3 points in on the triangle, okay, And if you draw those circles, right, let me call them points DEF. So the Miquel's theorem says that circles BDF, CED, and AEF are concurrent. That is what Miquel's theorem says. That if I consider this circle BDF and CDE, so, so that is a kind of very straightforward angle chasing. If you look at this point O and look at all the angles in the diagram, it is very clear that by simple angle chasing you will get it, because what will happen, this angle is equal to this angle by the first cyclic quadrilateral, and by the second quadrilateral this is also equal to this angle. So therefore the first and the last angles are equal, and therefore you can draw a third circle passing through AEOF. Okay, so this is typically what the Miquel configuration starts from. And then as a sort of property, they derive the fact that O is the center of spiral homothety around which, so in this diagram, the triangle DEF is the, like our PQR, right? And so from here, they derive the fact that O can be the center of a spiral homothety for any such triangle DEF. So what they say is that you can change this point D and DEF on the sides of your triangle. And as long as the shape of DEF does not change, the position of O will also not change. Okay. We are just deriving that fact in the reverse direction. So we started from the that assumption of constant shape of DEF to deduce that these three cycles as these are cyclic quadrilaterals. Okay, but either direction is fine. So I mean, I would suggest you to spend more time with this Miquel configuration. It is a very powerful idea, and it has also some relation to the four lines in general position which you may have studied. So how the general position lines are mapped to this exactly, I will may talk it some other lecture in the future. But for now, I just wanted to illustrate this. Uh, so I mean, just to conclude on our question, that we wanted to find the triangle, equilateral triangle, which has the smallest size. So the way you do that in this diagram is, I mean, we already showed that in GeoGebra, but just to show it here also. So there, what you have to do is choosing the O as my center of spiral homothety. I need to construct the smallest such triangle, right? So if I minimize the distances OP1, OQ1, OR1, right? If I drop perpendiculars to the three sides. So the interesting thing is that, and in general, if you take any point inside the triangle and drop three altitudes, you are not going to get an equilateral triangle. But that is the specialty of this point O, that from this point O, you will get an equilateral triangle. Although it doesn't look like it in my diagram, but this will be equilateral and it will be equilateral of this smallest possible size. Okay. And again, why is it going to be equilateral? Because again, by the fact that you are going to get the cyclic quadrilateral. So because of that cyclicity, you can conclude that it has to be equilateral. Okay, so this was one application of spiral homothety, but there are many applications to be studied. So I mean, we will continue to study spiral homothety for at least another one lecture, maybe even more than one lecture. And I mean, just to illustrate some more ideas that spiral homothety kind of helps us to deal with, like um, like we have already seen that similar triangles, right? Whenever you have similar triangles, spiral homothety has a lot of things to say. We also have intersecting circles. Okay, this is another important area where we'll see that spiral homothety is useful, because just to illustrate the point, if you have two circles which intersect, you can think of this point of intersection as the center of spiral homothety, which will take the first circle into the second circle. And so that finding out what is the angle of rotation, how much is the ratio of dilation, and all of those things will give you a lot of interesting properties. So this is another situation where spiral homothety is very useful to study. And the another point is complex numbers. So again, like we have already seen in one of the previous lectures that how rotation can be thought of as multiplying with a complex number of magnitude 1. What spiral homothety does is it will allow us to multiply with arbitrary complex number. So any two complex number multiplication can be described in terms of a spiral homothety. So that is the geometric or algebraic interpretation which I would like to give next time. Okay, so maybe I'll plan to end early today because just to give you some time off. Anything else that you would like to discuss today? And maybe one more thing to mention, I don't know how long we'll be continuing this series of lectures. My plan is to do it at least until the end of January because I think in my exam is towards end of January. After that, maybe February, March, you will be busy with your board exam, school exam. So maybe we have to stop this activity towards end of this month. But that gives us at least 4 or 5 more lectures to do a few topics, and we'll see how to keep in touch after that. But at least that is the plan for the this coming 1 month. Okay, then I think that's all I wanted to talk about today. So thank you all. Happy New Year and see you in 2024.
Bye, sir. Thank you. So happy New
Bye,
Year.
sir. Happy New Year.
Bye, sir. Thank you, sir.
Thank you. Bye.